Well, hello again, IB Juniors. That day has finally arrived, the last lesson of the school year. So this is it. This is going to be the last time you have to watch one of my videos for a little while. It's going to be the last time you have to do some homework for me for a little while. It's going to be the first time you start missing me for a long while. I know you're going to miss me. You really are. But well, we can cry about it later. Right now, we're going to get to these notes. So this last lesson of Unit 14 really pulls together all the geometry of the first and second derivative and how they relate to the regular function f of x. And it's just a bunch of drawing, to be honest with you, reading the graphs and seeing what it tells you. The homework is not that bad. I checked it out. It's a lot like these notes, and these notes are brand new for you guys. You're going to be the first ones that have seen 2 of the 4 examples. I created them right before I made these notes, just so you have lots of good examples. So this first one, what we have here is we have a graph of f of x. It's some wild looking graph. Our job is to use this graph to sketch a graph of what the first derivative could look like and what the second derivative could look like. So I'm just going to label, we know that this one's f of x. And I'm going to look at it, and first thing I'm going to notice is that, well, since both endings point up, I know that my leading term has to have an even power. And there's no way it's a parabola, right? Because it's got too many bumps. So based on its shape, since it has one too many bumps, we can safely say that it's probably an x to the 4th type graph. I mean, I'm sure it's got a lot of other terms in its equation, but we know that overall it's an x to the 4th type. It's a quartic. And now what we're going to do is we're going to start identifying some what would have been critical values had we actually had the equations that we could find the first and second derivatives of. And the way we do that is we identify places on f of x where we see flat spots, here-ish, and here-ish. And places where we can see, relatively see, it's not exact right now, but places where we can see a change in concavity. And I had just a few people get on Zoom with me a couple days ago, and the way that I demonstrated this was I tried to cover it up. So if I were to do this, oops, you can see to the left of my hand, sorry about that, hurt myself cooking, but you can see to the left of my hand, you've got an upward shaped bell. So, concave up. But then, somewhere here, we change from a downward bell to an upward bell. That means somewhere here, there must be an inflection point. And since we're not flat here, we know this would be a non-stationary inflection point. I'm going to say it's here-ish, okay? Like that. All right. I'm going to call this point on the x-axis A. And I'll call this point on the x-axis B. And this one we'll call C. All right, now, anytime our graph is flat, that means we have a slope of 0. Which means if you were graphing f prime's y values are actually the slope values of f of x. So at this point right here, f of x has a slope of 0. That means it is an x-intercept of f prime of x. And then right here, again, f of x is flat. So it has a slope of 0, which means f prime of x has a y value of 0. Like that. So what do we know? We know f prime of a equals 0. And you know what? Upward shaping bell, downward shaping bell. That means that A is also an inflection point. So this is a stationary inflection point. That's pretty cool. Okay, so before we get too far into that, let's go ahead and sketch what f prime has to look like. Well, since f of x is a fourth degree polynomial, f prime of x is a third degree polynomial. And more powerful than that, since this is a positive fourth degree polynomial, because the endings point up, this would be a positive third degree polynomial. So we can pretty much just sketch it. I mean, positive third degree polynomials, we should all be pretty much comfortable with what they look like, but they're going to go left, down, right, up, like that. And our job is to just connect this stuff in the middle. Well, let's see. Let's talk about our slopes. Everywhere to the left of A, your roller coaster would be falling if you were riding it, which means you have negative slope values. That's why the red curve exists down here. After A, though, your roller coaster is still falling all the way to point C. So between A and C, I'm still negative, but I do have to come back up to here. So it's going to look like this. Something like that. And you know, this would have been not bumpy right there. So this is what f prime of x could look like. Now, it wasn't an accident. Oh, I guess I should finish saying, you know, after point C, your roller coaster starts climbing again, which means you have positive slopes, which is why f prime exists above the x-axis, right there. Okay, so anyway, it wasn't an accident that this thing had a bump down here. Those correspond to one another. Oops, I put that dot in the wrong spot. Oopsie poopsie, it should have been right there. You see right here, at this spot, the red graph has a flat spot. That means its slope is 0. So if I'm trying to graph the second derivative, now I'm looking at the slopes of the red curve of being my y values of double prime. So I have a 0 here and here. Since f prime of x is a positive x degree or positive third degree polynomial, then f double prime is a positive quadratic type graph. Well, positive quadratics, both ends point up, right? So let's talk about the slopes here. If you're riding the red one as a roller coaster now, you're climbing, climbing, climbing until point A. Those are positive slopes. So you would exist above the x-axis. Now, your roller coaster would be falling from A to B, which means your slopes are negative. But then after B, you're climbing again, which means your slopes are positive again. So, like I said, negative, positive, like that. And this is what double prime could look like. So just to recap, f prime of A was 0, and that's because it's a flat point. F prime of C is also 0 because it's another flat point. When we went to go to the red curve, f double prime, meaning the slopes of the red curve now at A, was also 0. So what we have here is a critical value that showed up on the first and second derivative. So A would be a stationary inflection point, which you could see right here in the picture, but there it is showing up in the first and second derivative. And we also had that f double prime of B was 0. And I just realized I was using lowercase letters on my left side and I used uppercase letters over here. Sorry about that. Anyway, that's how you do it. And it should be pretty obvious that you had changes in concavity. Like I said, downward bell, upwards bell, you know. So yeah, these are true inflection points. Point A is a stationary inflection point, point B is a non-stationary inflection point, and there she is. Okay, so let's do a harder one. And this one is, let's use the word busy. It's got a lot going on. It really, really does. So let's see. First thing I'm looking for is flat spots and identifying them. Here's a flat spot. I'm not going to label it yet. Here's a flat spot. Here's another flat spot. Again, not labeling them yet. And then one more flat spot. Like that. Okay. I've identified my flat spots. Now I would like to try to identify places where I see my bell shape changing. I mean, this is clearly an upwards bell, and this is clearly a downwards bell. That means somewhere between this flat spot and this flat spot, my graph changed from an up bell to a down bell. Where exactly, I'm not sure. So what I'm going to do is I'm going to say that it's happening here-ish. Like that. And now here, again, downwards bell, but then here, upwards bell. That means between this point and this point, I changed concavity again because I had to have gone from a down bell to an up bell. So I'm just going to say it's here-ish, just approximating at this point. And we have here a upwards bell and a downwards bell. That means somewhere between this flat spot and this flat spot, I changed concavity. Let's say it's here. There. This one has a lot of X values that I want to label. So we'll say, just to keep them in alphabetical order, A, B, C. Remember, I'm on the origin there. D, E, F, and G. Wow, that's a lot of points. Okay, let's see what we can do. First, what do we know? Well, we can see that the endings point opposite directions, which means our leading term has to have an odd degree, and we can count the bumps, 1, 2, 3, 4 bumps. So this could be a x to the fifth graph, but more specifically, since it's left, up, right, down, it's a negative x to the fifth graph. Well, that immediately tells us that the first derivative is a negative fourth degree type, which tells us that our second derivative is a negative third degree type. There, we're ready to rock and roll. Let's start plotting our zeros of f prime of x. Remember, f prime of x, it is plotting not the y values of this curve. It's plotting the slope values. So right here, my derivative is 0. So f prime of x is on the x-axis. Right here, my derivative is 0. So f prime of x is on the x-axis. Again, derivative 0 on the x-axis, derivative of 0 on the x-axis. F prime of x is a negative fourth degree type. Well, fourth degree polynomials, this is even degree, their endings point the same direction, either both up or both down. And since it's negative, we know they're both down. So we're going to get a shape that looks like this. Okay, now let's see what's going on. Well, I know I'm going to have to cross through and then come back down. But how did I know? Okay, well, let's talk about it. Between point A and point C, your roller coaster would be climbing, which means you have all positive slopes. But then after point C, your roller coaster is falling, so now you have negative slopes. So this is going to be like this, and then, yeah, I'm going to pass right through the x-axis here because negative slopes, and my slopes stay negative until I get to point E. So stay negative until you get to point E, and then after E, my roller coaster would be climbing again all the way to point What happened to me? I just got lost. All the way to point G. Climbing all the way to G. And after G, we're falling again. And that's why we have these negative y values, because slopes are negative. So negative y values on f prime. And so we just come up and go through like that. There. That, and this is supposed to have been nice and smooth. There's your f prime of x possibility. Pow. Well, it wasn't an accident that these things kind of lined up. Because right here, let's see, switch colors. Right here-ish is a flat spot on my first derivative. Right here is a flat spot on my first derivative. Right here is a flat spot on my first derivative. So this double prime, remember, f of double prime of x, its y values are the slope values of f prime. So since this thing has a flat spot, its slope, derivative, gradient, whatever you want to call it, is 0 here. 0 here. 0 here. And we know that it's a negative cubic. That means left up, right down. Left up, right down. If you were riding the red roller coaster, it has positive slopes because it's climbing until point B. That's why I'm above the x-axis. Now from B to D, the red roller coaster would be falling. From D to F, the red roller coaster is climbing. And then after F, it's falling, which is why we have all negative slopes. And this could be a double prime of x. Mr. M, how do I know how high up to take the bumps and how low down to take the bumps? Look, you don't. There's a reason why they give you y values. You don't need to. It's just a guess. It's a general shape, okay? So don't worry about that. It doesn't matter how far down you went or how far up you went. Unimportant. What matters is that you hit the x-axis in the appropriate place and you have changes in concavity in the appropriate places. Okay? Okay. There. Now let's flip them over. Now for these ones on the back, rather than starting with f of x, we're going to start with f prime of x. And our job now is to just sketch a graph of the original function. So we're not even going to bother with the second derivative. We're going to talk about it, but we're not going to draw it. And I'm going to do these ones slightly different. For these, I would like to use a sign diagram. And that's because, well, I already have f prime of x. So let's draw the sign diagram for f prime of x. This is the f prime of x sign diagram. Okay. Let's see. There's numbers on this picture. We don't care. Numbers, unimportant. So let's just put letters there. We've got a point here. We have an x-intercept here. We have an x-intercept here. Then we have flat spots here and here. All right, let's track these down and up like that and name them A, B, C, D, and E. All right, so the sign diagram for f prime of x is talking about where is it positive, where is it negative, not its slopes, where is it positive, where is it negative. So those changes are going to happen at A, C, and E. So those are going to be the only three letters I put on here. A, C, E. So to the left of A, I'm below the x-axis. That means all my values are negative. I'm not talking about the slopes of this curve. I'm talking about its actual values. Between A and C, I'm above the x-axis, so all positive y values. Between C and E, I'm below the x-axis again, and after E, I'm positive. So what does that tell me about the original function? Well, that tells me, because I changed from negative to positive here, I have a minimum on f of x. Because I changed from positive to negative, I have a maximum at C, turning points. And again, from negative to positive, another turning point, a minimum. So we know that that's the general shape of f of x around A, C, and E. All right. Since f prime of x happens to be an x to the third type, it's a positive x to the third type, we know that our original function, f of x, must be a positive x to the fourth type. So that means both endings will point up. We know that. All right. What else do we know? Well, we can see that we have flat spots on our first derivative. So now let's draw the sign diagram for double prime. We're not going to sketch its graph, but we will draw its sign diagram. So this one is only going to have points at B and D. And I am trying to line these up appropriately. B, which happens to be between A and C, and D, which is between C and E, like that. Now, because I'm talking about a sign diagram of f prime of x, or f double prime of x, excuse me, I'm using the slopes of f prime of x now. Again, because this is f prime of x, every one of its y values is actually a slope of f of x. But its sign diagram is showing me its actual y values. Now, when I go to the second derivative, now I'm talking about the slopes of this curve. So, if you're riding this roller coaster, you're climbing until B, so it has positive slopes. From B to D, you're falling, which means you have negative slopes, and after D, you're climbing again, positive slopes. So what does that tell us? That tells us in this area, I am concave up. In this area, I'm concave down. And in this area, I'm concave up again. There we go. Time to start sketching. What color do I want to use? Whatever. Let's use blue. Okay, let's use some blue. We know for a fact that we have both endings pointing up. We know that our curve is stationary here, but it has a minimum. So I'll just kind of do like this. I know I have a minimum on that green line. I know that I have another minimum, I know that I have another turning point, which would be a maximum at C, and I have another minimum at E. Minimum, but both endings are up. So I'm going to pick an arbitrary y value, I don't know, and we go up and, I don't know, up, okay, like that. We know at point C, on this green line, I have a maximum of some sort. And right here on B, I'm going to have a change in concavity. So let's see if I can pull that off. There we go. That was pretty close. Now I know that I have another change in concavity at D, and I have this minimum down here, so I have to connect like that, but I'm going to try to get my concavity to change on... That's pretty close. That's pretty close. So that could be an f of x. How far down, how far up, how far down, who knows, who cares? Unimportant, okay? Okay. Last one, and again, a little bit more challenging than the one that we just did. I tried to make them challenging. Ooh, kind of bled through the paper right there. Oh, by the way, your homework is down here. Page 338, 339, 123. That's all the questions. It's like 6 questions, okay? Okay. Here's the exact same idea. This is an f prime of x. And our job is to sketch the original. So what do we see? We see a flat spot right here. We see a flat spot right here. By the way, this is also an intercept. This is an intercept because this is f prime of x. That actually matters. Because remember, when you cross through the x-axis, you have a turning point because you just went from positive to negative on the original. So this is a turning point. Here I have a flat spot, and here I have another x-intercept. So let's see. Point A, point B, the origin is point C, point D, and then point E, like so. Okay. What do we see? We see that f prime of x, both endings point up, which means we have an even degree, and I see 1, 2, 3 bumps, so it is a positive x to the 4th type. That means f of x is a positive x to the 5th type. Neat. Okay, let's see what we can do. Remember, odd degree polynomials are left, down, right, up when they're positive. So that's what it's going to look like on its endings. Let's do a sign diagram for f prime of x. Sign diagram is going to include the areas where we hit the x-axis for f prime of x. So A, C, and E. A, C, E. And remember, what we're doing is we're actually talking about whether or not f prime of x is above the x-axis or below the x-axis. Because when f prime of x is above the x-axis, that means your slopes are positive. When f prime of x is below the x-axis, that means your slopes are negative. So to the left of A, since I'm above, I'm positive. I have positive slopes. But now between A and C, I'm positive again. That's interesting. I have a spot on the first degree's sign diagram, or not the first degree, the first derivative sign diagram that is not a turning point. By definition, it must be a non-stationary inflection point. Excuse me, a stationary inflection point. Stationary because the first derivative is 0. From C to E, because I'm below the x-axis, I have negative y values on the derivative, which means I have negative slopes. And then after E, I'm above the x-axis, so I have positive slopes. So a stationary inflection point that's positive, positive will look like this for the original, positive, positive. Now this is positive, negative. So I'm going to have a maximum at point C, and this is negative, positive. So I will have a minimum at point E. We know all that stuff. Now let's draw the sign diagram for double prime of x. Now we're actually talking about the slopes of this curve. So its flat spots are important to us. I have a flat spot at A, trying to make it line up perfectly with A. And look, the same value showed up on the first and second derivative sign diagram, which automatically makes it a stationary inflection point, but we already knew that. I have a flat spot at B, which happens between A and C. And I have another flat spot at D, which happens between C and E. Now we're talking about the slopes. If you're riding this roller coaster, these slopes, this is going down, so these slopes are negative. If you're riding this roller coaster, you're climbing from A to B, so its slopes are positive. If you're riding this roller coaster from B to D, this roller coaster is falling, so it has negative slopes, and after D, it's climbing again. So anytime you have a change in concavity, you have an inflection point of some sort, right? So all 3 of these are inflection points. But this one only showed up. This is the only one that showed up on both. So we already know that this is a stationary inflection point. And because I have a sign change here, this is an inflection point, but it didn't show up here. That makes it a non-stationary inflection point. And same thing here, non-stationary inflection point. Here, we're concave down. Kind of running out of space here, so I'll do CC down, CC up, concave down, and concave up. I'm cheating a little bit. Let's get her sketched. Alrighty. I know that I'm going to be left down, and I have this kind of shape happening at point A, so might as well go ahead and make that happen. Like this. Now, I didn't go too far because what I have to remember is that something is happening at B. I have a non-stationary inflection point occurring at B, but then I have a maximum happening at C. So I have an upwards bell and a downwards bell, and I kind of need that to happen right here on this dotted line-ish. So let's see. That's pretty good. Now what's happening? I know I have to come back down, and I know I'm going to dip at E. So at E, I have a minimum. No, what just happened to me? Yeah, at E, I have a minimum. Sorry. Couldn't read my own handwriting for a second. And that's going to occur just anywhere along an E dotted line if I wanted to draw one. There's going to be a minimum somewhere. And there will be a change in concavity at D, on the D line somewhere. So let's see if I can make that happen. So down, change in concavity, dip, and then climb. I never claimed to be an artist, but there it is. That is a possible f of x. And I hope you enjoyed this as much as I did. I'm pretty sure that you're going to probably have to pause it a lot and re-listen and hear it again. And you know what? There's absolutely nothing wrong with going onto YouTube and looking up other videos like this. And I suggest going to YouTube and looking up first and second, or like derivative, questions, former IB questions, or like look up, IB concavity, things like that. Just look and see what kind of videos you can find. And as usual, I'll be having a Zoom Thursday morning, let's say 11 o'clock. So let's plan a Thursday at 11 o'clock Zoom for anybody that's interested. And hopefully I will see a lot of you there. Have a good one, folks.